Hello everyone, welcome to the paper presentation for Can 5G millimeter wave support multi-user AR. I am Moinak and this work was done in joint collaboration with Pranab, Zhao Chang and Charlie from Purdue University, Dimitrios from Northeastern University and Yuanji from Tsinghua University. So what is multi-user AR? As you can see in this video, multi-user AR allows multiple co-located users to interact with virtual objects in the same physical space. It is mainly an uplink-oriented application, and most of the multi-user AR applications has a cloud-based architecture. It relies heavily on cellular network for user interactions, and hence it requires low latency for high-quality interactive experience. In a previous measurement study of multi-user AR performance over LT, the authors found out that the high end-to-end latency degrades multi-user AR performance. They observed a median latency of 12.5 seconds, which could go up to as high as 27 seconds. They proposed two optimization techniques to improve performance. Today, 5G millimeter wave is being rapidly deployed by major US service providers. 5G millimeter wave provides 10x and 3x more downlink and uplink bandwidth respectively and has lower latency compared to LTE. However, 5G millimeter wave is heavily affected by blockage and mobility, which in turn affects the network performance. So we ask a very basic question. Can 5G millimeter wave provide better support for multi-user AR compared to LTE? Our contributions are as follows. First, we perform an in-depth measurement study of multi-user AR over commercial 5G millimeter wave network. We also study energy consumption of multi-user AR over 5G and LTE networks. Let us look into the cloud-based multi-user AR architecture. So the host places a virtual object on the screen and the resolver should be able to see the same virtual object on their own screen. So when the host places the virtual object on the screen, it establishes a connection to the cloud. Now the host uploads its visual data to the cloud, and when it's done, the cloud processes the host's visual data and sends back the SLAM computed world frame to the host. It also notifies the resolver to send the resolver's visual data to the cloud. The cloud, on receiving the resolver's data, tries to match them against the host's data and estimate the pose of the resolver in the world frame and sends it back to the resolver. The resolver then uses the cloud process data to render the virtual object on the screen. Let us look into the latency of the components I described in the previous slide. We performed measurements over 5G while facing the base station as well as while facing away from the base station to emulate blockage. We perform measurements over LTE, and for comparison, we show the latency values put forward by the previous work. In comparison to the previous work, we observed that the end-to-end latency has gone down a lot. However, this latency is still high for multi-user AR to function properly. We see that the median latency is around 5 seconds, and it can go up to as high as 10 to 14 seconds. Interestingly, 5G does not provide better support compared to LTE as well. We observed that the major contributor to this end-to-end latency are the components 1B, 1C, and 2X. In the previous work, the authors mentioned that 1B and 1C were the major contributors to the end-to-end latency. However, they did not observe the additional delay or the delay 2X. It is the time from when the cloud finishes processing the host side data and is yet to notify the resolver. We see that this delay could be as low as 100 ms to as high as 7 seconds. We conjecture that this delay is due to various middle box policies implemented by the cellular network provider. In terms of uplink communication, we observe that 5G millimeter wave has lower latency compared to LTE. And however, this difference is small because the application uploads very few bytes and does not allow TCP to exit the slow start, and hence the high bandwidth of 5G remains unutilized. Interestingly, LTE outperforms 5G under blockage. In terms of cloud processing, we observed that on the host side, it takes around 2 seconds, whereas on the resolver side, it is negligible. But sometimes cloud processing can fail and the resolver has to re-upload the visual data. This latency can be as high as 5.5 seconds. We also studied two optimization techniques that were proposed in the previous work over LTE networks. For 5G millimeter wave network, the packet size adaptation had no effect, but for small background traffic introduced during an AR session, the performance did improve. For more details on the optimization techniques, please refer to our paper. Let us look at the energy consumption of multi-user AR. 5G millimeter wave drains 28% higher total energy compared to LTE. The host side consumes more energy than the resolver, and the network energy is the major contributor to the total energy. So to conclude, we found that 5G millimeter wave, though it has higher bandwidth compared to LTE, does not improve multi-user AR performance. There are two reasons for that. First, the application uploads small data bursts that do not allow TCP to exit the slow start. As a solution, we recommend using TCP splitting and set up a proxy that maintains a persistent connection to the cloud server. The second problem is that apart from the communication latency, there are other delays that are independent of the network technology. They are also the major contributors to the end-to-end delay. The first is the notification delay, and the second is the cloud processing delay. To reduce the notification delay, cellular operators should revisit middle box policies in their packet core networks. To reduce the cloud processing delay, we provide two recommendations. The first is either move cloud processing to the edge servers, and the second recommendation is to shift to a P2P paradigm completely. In terms of energy, multi-user AR app consumes 28% more total energy and 66% more network energy over 5G millimeter wave than over LTE. Thank you.